Time to ruin the video with some talking. So this is a companion video to a recent paper that we released sort of in this intersection of geometry and autoencoding. However, the paper is long and dense. So I thought it would be nice to have this companion video to help present what we've done in this paper in a more digestible way. Okay, so this is the structure of this video. The first part is just talking about why we're motivated, about what we're motivated about, what are these tiny little dancing strings, and how are they going to generate me neural network autoencoders for my data. Then we'll obviously talk about the paper itself, the methodology we introduced, and some of the results, just how to see what we did and how we view this as being important and potentially impactful. And then finally, future work. What are the future directions for this work? And in my, of course, unbiased opinion, there are a lot. Okay, let's dive in. Motivation and problem formulation. This will be two main parts. First, I'll talk about the manifold, the geometry side of it, and then I'll talk about the deep learning or autoencoder side of it. First, we need to talk about what is the manifold hypothesis. So the manifold hypothesis is an assumption about the structure of learnable data in the world, and specifically learnable data that is vectorizable in some way, which pretty much all data for deep learning is. What do I mean? It's that your data is a vector in some way. So like 3D coordinates is a three-dimensional vector. Images are, if we take like, for example, 1,000 by 1,000 grayscale images, this can get flattened out into a million-dimensional vector. And words or tokens usually get embedded into a word or token embedding of some size and shape before getting processed by a transformer. Now, when your data is vectorized, it means every data point is sort of like a point in some space. Here is my attempt at drawing 3D coordinates. And so a data set is just a set of points. Finally, the manifold hypothesis is saying that for learnable data, your data points lie near some low-dimensional submanifold of the data. It's a lot of word vomit, but let me give an example here. So let's go back to the images. These are at 1,000 by 1,000 grayscale images, and let's say you're tracking the position of a ball. Now, each image of a ball is a million-dimensional vector, but this is not a million-dimensional problem. How many numbers do you need to describe the position of the ball? Well, you need two. It's x position and its y position. So this data set of images of balls at different locations is a two-dimensional manifold. And the assumption is that for any learnable data, they all have this low-dimensional structure like this. Okay, that's manifold hypothesis. You can read more. There are lots of wonderful sources out there. I will link one. Jumping back to the examples shown at the beginning of the video, this is an example of what data could look like. It is, in this case, a one-dimensional manifold. These are your data points that lie in two-dimensional space, but near a one-dimensional manifold because there's only one direction to move along. You need one number to describe where you are along the sine wave. Okay, that's the manifold hypothesis. Now a little bit about autoencoders and why we view these as important. First, what is an autoencoder? Well, if you have your data X here, usually the purpose of an autoencoder is to train two neural networks, F and G. F is mapping your data into a much lower dimensional space, Z. So if your vectors were a million dimensional here, they could be 100 dimensions in Z. And the role of G here is to then reconstruct from those 100 dimensional vectors back to the original data in a million dimensions. Why are these important is because we're now starting to learn and practice a lot in deep learning that a fundamental part of learning itself is this sort of Occam's razor principle. For humans, you can think of the Z as what goes on in the brain. When you learn the simplest explanation of the data, this is often what generalizes the best, whatever you've compressed the most. So what happens now a lot in deep learning frameworks, one famous example being Stable Diffusion, is you first train an autoencoder like this, and then you just run your learning model in the Z space. So if you're training an image classifier, instead of staying in this million dimensional space, you learn your autoencoder and you train a classifier in the 100-dimensional space, which is obviously more computationally efficient, but we also hypothesize that these representations are just better for learning and generalization overall. Okay, great. That's why we care about both of these things. Now let's get into the paper itself and what we actually did. First, what is the problem that we're addressing in our paper? Well, we want to construct a minimal autoencoder from a data set. And we've sort of written in this data matrix form. This is basically just saying your data is of dimension D, and we've stacked n of these data points into a matrix. Okay, what does a minimal autoencoder mean here? It means over all autoencoders, the dimension of the Z space is as small as possible. We've compressed as much as possible. This is truly like the Occam's razor principle for autoencoders, the smallest or simplest explanation of the data being the best thing. So this is what we want to do. What is known about this problem? How do we solve it? Well, the linear case is solved. Basically, what do I mean by the linear case? If you have some subspace, in this case, it's a two-dimensional subspace, and your points all lie densely within that subspace. Right? This problem is solved by PCA. You get whatever principal components that you've constructed from the data, you multiply by U, or U transpose in this case, and then multiply U back to get your data back. The Z space is the lowest possible representation of your data, and we have done this minimal autoencoding that we set out to do. Okay, for the nonlinear case, what if we just reduce it to the linear case and then solve it there? So if you have a nonlinear data set like this sine wave, what if we just iteratively kind of massage out and learn how to reconstruct back these nonlinearities until eventually we get to something that is fully flattened and we just do PCA in the flattened space. This is indeed what I was showing at the beginning of the video. This is our method running on these synthetic manifold data sets where we are taking a nonlinear data set and making it linear by running this flow and also remembering the reconstructions, which we just didn't show in these GIFs, but they're still happening alongside. Now, this final flattened space is our geometric interpretation of disentangled or intrinsic representations. The idea is you've gotten rid of the nonlinearities. What remains is only the true intrinsic structure of the data itself. How does the new autoencoder look here? Well, there's just one extra caveat here. You take your data and you first run this flattening process in the ambient space to get something that is now linear. You then just do PCA. And then finally, we've constructed these local reconstructions. So we just run that process to get back to the original data. So this is the new autoencoder structure for this method. Now, finally, how do we actually do it? Because this is probably the main source of convolution for the paper. And the source of this convolution comes from the fact that we want to be as general and assume as little as possible. We should just have a process that you throw it at a data set and it does it. It compresses it as much as possible. You do not need to tell it the intrinsic dimension. You don't need to tell it anything a priori about your data set. So since we're not telling it these things, these are sort of things we have to learn about the data as we go. Okay, let's get into it. At every step of the flattening process, here's what we do. First, we choose a random point on the manifold. Let's say we chose this. This is sort of why the GIFs, they look a little bit jittery, because we're constantly jumping around the manifold. Then what we want to do is first find the dimension around this point. So this is a local problem. We're going to take a small radius and only consider points in that radius. So for now, we're going to ignore the rest of the data set. How we find the dimension here is we want to learn the smallest quadratic model that still explains the data in here. What we're using is that for manifolds, in some radius, we expect it to look close enough to some quadratic model. So we can use this to do a sort of almost a local autoencoding problem. And this, in turn, will sort of give us the dimension. Now, what do I mean by all of this? Let's start with dimension 1. So the data set in here, we'll call this xloc or xlocal. And first we want to find a one-dimensional, fully linear coordinate representation. So we hit it with a normalized vector U transpose, and now we get a coordinate for each data point. C1, C2, C3, so on and so forth. These are all scalars. Now we want to feed these quadratically as output to try to reconstruct what we've lost through this linear flattening. So for each xi, our reconstruction is equal to some vector v times its coordinate squared. Now there are two learnable components here, the vectors u and v. You can optimize these to get the best one-dimensional quadratic representation. And this optimization is quite straightforward. It works quite well. This is a very nice structured data set because we're very local. Once this converges, you'll know if it's good enough or not, and then you can choose to add another coordinate. So now we're going to stack two vectors into an orthonormal matrix. So now each of these coordinates is a two-dimensional coordinate, right? Some A, B, some C, D, so on and so forth. And this is going to change as well. I won't write it out here to make it complicated, but now we have a two-dimensional quadratic model, and we try to optimize this. And we eventually go up until we fit a local quadratic model, and that will be the intrinsic dimension of the manifold at that point. Okay, so this is all step 2. Step 1 is picking the point. Step 2 was finding the dimension through this local quadratic model. Now we're going to consider the rest of the points, because step 3 is finding what is the largest radius that this model fits. If we can flatten more of the manifold, then we'll flatten as much as we can. So we can optimize this as well. This is another smooth optimization. And let's say we eventually settle on this radius, that the quadratic model fits well. Well, we have a model of our data now, so we can do whatever we want with it. We can flatten it in, we can remember how we reconstructed and reconstruct back to the original data set. And finally, we have what we were working for. At that point, we have constructed a flattening and reconstruction that will generally massage this manifold to something that is globally linear. So when the GIF is playing, this whole process is happening at each little step over and over again until the whole thing becomes flattened. There are lots more details in the paper itself, of course, how this is all carried out, how we can sort of guarantee that this thing will flatten globally. Obviously, it doesn't always, but we sort of have some intuition on when it can. And then we get what is now shown in these GIFs. Okay, this is sort of an ideal case for this method running. The blue points here are the original data set. And you may notice it's not exactly in the manifold, it's a little noisy. This is sort of how we expect real data to look like. After running this process, you get the flattened data, which are these X points. And because we've learned global maps for all of this, you can interpolate between those training points and get the smooth green curve as our reconstruction of the original manifold, which looks like the noiseless version of where this data was generated from. You may notice there's a little bit of off-tail behavior at the end. This is sort of the compounding errors problem because we're doing these local inversions. Now, certainly for future work, there is room and a lot of easy improvements to make the global reconstruction better. For this work, we're focusing on the representation. If you go back to this autoencoder framework, we are trying to get these sort of flattened, what looks like the intrinsic representations of the data, which we hope will, at the very least, improve performance for downstream learning. Of course, you can run this process on any vectorizable data, including things like images. Now, what's shown here is not the flattening process, but what interpolation looks like when you don't flatten it versus after flattening. So in this bottom is if you were to linearly interpolate these two images, obviously you have some fading effects that go on in the middle, and the top is if you were to flatten the data using our process and then interpolate in the flattened space, which now this middle two does look like an actual two. It's sort of an actual image interpolation between the two. Now, I'm not going to pretend like MNIST is a state-of-the-art competitive place to show autoencoding performance, but what is impressive and what is impactful here is that to get this autoencoder, we just kind of let this, the equivalent to the GIF, we just let this flattening process go. We didn't choose network width or depth or stopping time or anything like that. It automatically compressed it to 12-dimensional features, which is the currently theoretically accepted dimension of MNIST without having to specify anything. So if autoencoders continue to be a crucial pipeline for learning frameworks, then now your autoencoder just gets generated on its own and built up almost like an organism or a brain that's building up the network on the fly, which I think here is super cool. And there's a lot of very, very cool stuff to do here. Okay, so what are these exciting things left to do? Besides this global reconstruction problem that I do think is low-hanging fruit, there are a couple of main areas that I think there's a lot of interesting research to be done. One is scaling. We've designed this method to scale, for example, linearly with number of data points and the extrinsic dimension. And there are lots of ways that you can sort of parallelize this process. So for example, disjoint neighborhoods can be run on parallel devices. These are just things that we have not implemented yet. And I think there's a lot of interesting work and research to do along those directions. Not only scaling up the data set though, but to different domains and problems. So for example, nonlinear regression. Well, a function graph is a manifold in itself. So you can run the flattening procedure on this, then do linear regression, and suddenly you have a nonlinear regression algorithm. There are some caveats, of course, with the domain and range of the function, but there are lots of interesting ways to extend this kind of methodology in research. And the other is the geometric aspect of this. So the manifold hypothesis is, at this point, a little bit older, and it's perhaps a little bit overfit from the differential geometry and all the power that's been made for physics and for pure math. So why do we overfit this? Well, there are two things about real data that are definitely quite true. One is that it's very low dimensional. With everything we see in the world and learnability and compression, this is almost at this point seems like a complete fact. So the data that's learnable is low dimensional in nature, and it's also geometric, right? At its core, geometry is studying how points and sets of points relate to each other, and these structures have structure, right? And geometry is sort of the way to exploit that structure. But jumping to manifolds being that structure, there is a lot about this image that I just drew here that you're assuming. So these sort of low curvature regions, for example, images and translations, these are very, very rough if you were to be able to visualize them. The fact that it has to be the same dimension everywhere on this manifold is also a bit of an issue, right? So your threes have to be the same dimension as the sevens. Even if you were to do like a union of manifolds or a multiple manifold hypothesis, different manifolds have cross dependencies and cross structures with each other. So for example, dogs and cats have structures as what we would call quadrupeds. If you saw a dog running, you'd be able to impinge that motion onto a cat or any quadruped that I showed you a picture of. So the geometric structures of data need to be modernized past the original differential geometry, which has a very vast toolkit, but one that was developed for pure math and physics. And these are very different manifolds than the ones that or different geometric structures than the ones that we deal with in real life. So this is what I think is interesting to do. That's it for me. I'm super excited about all of this. If anyone else is excited as well, whether you want to do research or just ask a question, please reach out. Love talking about all of this at any time.